Okay, so we've been spending some time on linked lists. I want to talk about another data structure for storing a list of elements. And that's just the list. Okay, so I'm going to talk about how Python implements a list behind the scenes. And actually, Python's list is roughly equivalent to Java's array list and C++'s STL vector, if you remember that. Okay, I say roughly equivalent because the Python list is even more flexible because you can basically store any type in it, right? But they have the same behavior as data structures. Okay. So let's see why. You know, this is going to be more flexible than an array. So if I make an array, I can actually add things to the end of it. Oops. 10, 20, and I can also pop things. So I can actually take things off the end of the list. And we see, okay, I added 10, I added 20, then I took 20 off, and then I was left with this. So if you remember, for an actual array in Java and C++, if you want to remove or add elements, you actually have to make an entirely new array. So if you want to remove an element, you have to make an entirely new array. Copy everything over except for the last element. Okay. Yeah, so if you want to remove the last element, you have to make an entirely new array one size smaller and then copy everything over except for the last element. If you want to add something to the end, you also have to make an entirely new array, one size larger, copy everything over, and then put in that new element. So these always are going to cost O of n if you're going to do them on arrays, because we have to make a whole new array just to add one thing. Okay, so the list data structure is going to be a little smarter than that. And we're going to have to hedge our bets a little bit though. So we're going to get something that is O of 1, but looked at slightly differently via a lens called amortized cost. Okay, so I'll talk about that at the end. But first, let's actually go in and start to make the data structure. So I'll call this an array list, just because Python already has something called a list. And I'm just going to start to make it. So even though I want this to be better than an array, I can actually use an array behind the scenes. So what I can do is I can create an array that maybe I have to resize. So I'm going to assume that the array stays fixed. So I have an array in the background, and I'm only allowed to make a new array or to modify the current array's elements. So I'm going to simulate, I'm going to kind of tie my hands behind my back a little bit and not allow myself to use this like a Python list. I'm really going to pretend it's an array. So if I want to add something, then I'm going to have to make a new array. Okay, so that's the only things I'm allowed to do. I'm allowed to make a new array of a fixed length, or I'm allowed to modify the current array's elements. Okay. Now, there's another thing though. So I can also specify capacity. So how many elements can this thing hold? And let me just show you, if I wanted to make an array of capacity zeros, this is a little trick in Python. So just to show you, if I say the array is equal to 0 times 10, this is going to make an array, and then I say, maybe I change one of the elements. Array at index 4 now becomes 20. If I print out the array, what you see is that made an array with 10 zeros, and I put 20 there. So this is the quick way to make an array of a fixed length that starts off with all zeros. Okay. Now, okay, but really when I make this array list, I want to think of it as starting off with no elements. So it may have a capacity, and you know, maybe I passed this along as an argument to the constructor. By the way, if I say capacity equals 10, that means by default I'm going to assume that you passed a 10 even if you don't specify. So I can say something like this. I can say L is equal to array list like that, and the capacity we'll see is 10. Or I can say L is equal to array list and actually specify something. Maybe I want a different capacity. It's 20. Okay. All right, but then let me actually remember how many things, it has a capacity, but let me remember how many things are actually in there. So this is how many elements we have. And so I can go ahead and make, I can implement the length function so that we can use the len on this in Python. Okay. All right, so now I've set up the skeleton for some data structure that's going to have a capacity, and I'm going to store a certain number of elements. So let me go ahead and make an add function, or an add method. So I'm going to say this is supposed to add an element at the end of the list. Okay. So x is simply the element to add, and it returns nothing. Okay. So first, what I should do is make sure I haven't run out of room. So I'm assuming I'm adding these elements in order, so I'm always going to add them to the end. So if I find that the number of elements is equal to the capacity, then I'm going to say list is full. Okay, I should actually throw an exception, but in the interest of time, I'm not going to do that. But otherwise, if there's room, what I can say is, okay, well, let me put this new element at index n. Right, if n starts at 0, if there are 0 elements, I'm going to put this in index 0. If there is 1 element, that means that I want to put this in index 1, and so on and so forth. So I can do that, I just have to remember then to increase the size by 1. Okay, so whoop-de-doo. I sort of like tying my hands behind my back, making a list that has a fixed size, but maybe that, you know, on the back end, but that I sort of keep track of how many, maybe I can add as many elements up to that size. Okay. So let's test this out. So I'll say L is equal to array list, L.add 0, L.add 1, L.add 400. All right, first of all, it runs, okay. Let me also create a function that exposes access here. So I'll say def, there's another way to do this in Python, but I'll just make it a little more like Java for now. So if you pass me an index I, then I'll return self.array at index I. Okay. And actually, because it's using a list as its underlying data structure, it will throw an out of bounds exception if you go beyond. Okay. So I guess I will also make a toString function just so we can see what's in here. So what I'll say is for I in range self.n, s plus equals self dot the underlying array at index I. I'll say if I is less than self.n minus 1, then I'll print a comma. I'll put a comma in between. I'll return s. So let's just see what I have here. Let's see. Why is it not doing the toString here? Oh, because I have to run this code again. Okay. Okay, I have to be a little more careful with my string formatting. I always forget this. Okay. So this is going to turn whatever is in the array here into a string. Okay. All right, so we see we got 0, 1, 400. Cool. So let's see what happens if I maybe do a loop. Let's see, for I in range 12, L dot add I. Okay, so it tells me twice. It tries to add 12 elements. As soon as it gets to trying to add 10, there's already 10 elements there. So it's going to print list is full twice. Just to show you something that's not exactly these. Okay, 0, 2, 4, 6, 8, 10. Okay. You know, I could make a bigger capacity, right? And then I'd be fine. But eventually, maybe I'd run out of capacity there too. All right. So this is not the end of the story, because you never, unless you run out of memory on your computer, it's never going to tell you something like list is full. So here's what we're going to do. We're going to do something a little smarter. If the list gets to capacity, we're going to do something else that we haven't done yet, but which we're allowed to do. So far, all we've done is modified elements in the array and remembered how many there were there, right? But we can also, we're allowed to change the array. So what I can do is, if I'm at capacity, here's a cool thing I can do. I can say self.capacity plus equals 1. Okay, so I'll make the capacity bigger. And then I'll say self.array is equal to, here's where I have to make a new array. And then copy everything over. So I'll say, or I guess, I have to make a different variable first. I'll say new array is equal to that. New array at index I is equal to self.array at index I. And then I'll say self.array becomes the new array that I just made. Okay. So I'm going to increase the capacity if I need to. I'm going to make a new array that's big enough to accommodate that many elements. I'm going to copy over all the elements that were there before, and then I know no matter what, I have enough room to add stuff here. So now I know I have enough room, no matter what. So I'm going to grow the list behind the scenes. Okay, to make space. So let's see if this works now. So it should never say list full. Well, I got rid of list full, but it should actually store all the elements that I put in there. All right, cool. So I counted in 2, starting at 0 up to 29. So that got me up to 58. So that seems to work. Very nice. But this is maybe not the best thing, because let's think about the cost that this takes. So up until I get to the capacity, so I'm going to actually call this add slow, because we can do much better than this if we think a little bit. So if we, let's say the capacity is 10, and we add 15 elements. Okay. So the first 10 adds are going to take O of 1. And the reason is because if we're not increasing the capacity, we always do the same two things. We change one of the indices to be this new thing we're trying to add, and then we update the number of elements that are there. So this is constant time. No matter how many elements are there, we always do these two, unless we have to increase the capacity. But if we have to increase the capacity, so after 10, all adds are going to take O of n, because we have to make an entirely new array before we do this constant time thing. Let me be a little more specific. So let's just say that, so let's assume that increasing the capacity 1 takes, we'll say some constant a times n plus 1 elements, where n is the number of elements that are there. And we'll say adding an element after that takes b operations. Okay, so for the first 10, we're going to take 10 times b, right? So 10 times b for the first 10. But after that, it's going to be, when we go to add the 11th element, it's going to take a times 11 plus, then plus 12, plus 13, plus 14, plus 15, and then plus 16. Okay. And then each time we also pay a cost of b, so that'd be b times 5. Sorry, we're adding up to 15 elements. Okay. So the last one's going to be 15. Okay, so there are 5 of these where I have to actually increase the length of the list, and it costs more and more each time, plus b times 5. So the total cost is 10 times b plus, really 15 times b. So it's 10 plus b times all this. 15 times b plus a times this number. 11 plus 12 plus 13 plus 14 plus 15. Okay. Now what you'll see is, if I want to know what's the average cost here. So actually let me just go ahead and, rather than beating you over the head with a formula right away, I'll just do this in code real quick. So 11 plus 12 plus 13 plus 14 plus 15. Okay, so that's 65. So this is 15b plus 65. So one thing I can ask is what was the amortized cost per operation in these first 15 ads? So in words that we already know, this asks, what is the average time it takes per ad? Okay. So this is going to be 15b plus 65a. So 15b plus 65a over 15. What's 65 over 15? It's not quite 5. It's a bit more than 4. Whoops. 4.33. Okay. So this is going to be about a plus 4. Sorry, about b plus 4a. But if we keep going, let's say that we add, let's say that we add n elements where n is very large. Then what you can say is, okay, so this cost is going to be approximately n times b, because b is how long it took to do these two at the end. So it's going to take n times b, n times b plus 1 plus 2 plus 3 plus ... plus n times a. Okay. So yeah, if I start off at a capacity of 0, then I'll have to do this step every time. But even if I start off at a capacity of 10 and my n is large, the rest of these are going to totally swamp the ones at the beginning. So this is a fine approximation. But yeah, I can really say that my timing function is less than or equal to this. Okay. Now there's a formula for this. 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 over 2. So let's check. If n is 1, well, 1 times 2 over 2, that's 1. If n is 2, 2 times 3, which is 6 over 2, that's 1 plus 2, which is 3. 1 plus 2 plus 3, if n is 3, that should be 6. 1 plus 2 plus 3, so 3 times 4, that's 12 over 2 is 6. Okay, so that's a good formula we can use. So what we're saying is our time is less than or equal to n times b plus n times n plus 1 over 2 times a. So we'll say bn plus an times n plus 1 over 2. And you can show that this is O of n squared, actually. So if we want to know the average time per operation, per n operations, this is the amortized cost, then we divide t of n by n. So we can say t of n over n is less than or equal to b plus n plus 1 over 2. So we can actually see amortized costs, T of n over n to do all these operations. So T of n is the time it takes to do all, so we're saying T of n in this context is the time to add n elements. And we're trying to boil down to, well, what's the average cost to add a single one? That's T of n over n. We call that the amortized cost. So we say that that is big O of n. Okay, so that's not good. If it takes, big O of n to add a single element, we're in trouble. This thing's really going to slow down as we add more elements. But there's a smarter thing I can do. And I'm going to want you to think about what the amortized cost is. So instead of saying, let me add 1 to the capacity, what I can do is if I run out of capacity, I can actually double the capacity. Okay, so if I had 10 elements and I'm trying to add an 11th, I'm actually going to go up to a capacity of 20. This is going to be much better. So I want you, first I'm going to have you just code up the remove method, which should be pretty quick. But then after that, I want you to think about what the amortized cost is if I'm doubling. Okay, so I'll guide you through that. And that's something that I want us to think about before class. All right.